Hey everybody, and welcome back to Algebra 2 Online. So the plan for today is just do a few review problems from our log and exponential unit. So let's just get into it here. So, one of the earlier things that we did in this unit was solving these exponential equations. And sometimes you get these nice ones like this where you don't even need a logarithm to solve it because there's a way to write 4 as 2 to some power, right? So we can do one like this where we do 2 squared is 4, right? And then we have all of that to the x squared and then over 2 to the x equals 2, right? And then it's just literally like properties of exponents. So you multiply these up here. So you have 2 to the 2x squared over 2 to the x equals 2. And then you subtract exponents here. So then that could be 2 to the 2x squared minus x equals 2. And then this is like 2 to the 1, right? And the only way this is going to be equal is if these exponents are equal now. So you can literally just go ahead and just work with the exponents. So 2x squared minus x has to be 1. And then this is just like a nice quadratic. It actually factors into this. And so then the roots are negative a half and 1, right? And exponentials are well defined everywhere, so you certainly can check it just to make sure it's correct, but it's going to be fine. If you plug these in, it'll definitely work. So that's kind of like the nice version of exponentials. There's definitely lots of times where you can't get the same base, like once you've simplified it. And if you got like 2 to something up here, but it equaled like 3 to something else, you just have to use logs. You could either use log base 2 or log base 3. And that would cancel off one of those, and then you can just use like log properties basically which are really just exponent properties, right? To simplify it and solve it from there. But this is like your nice case of exponential equations. Another really important concept from this unit is just using what we've learned about logs and exponentials to solve application problems. This is really the reason they pop up, is because there's lots of things that are modeled by them in the real world. And one of them is this, there's this exponential decay stuff with this carbon-14 thing. So we've seen this, and if you keep taking a lot of science classes, you'll see a lot more of this. But it's carbon dating is a very useful technique to basically see how much or how old something is. So this is like a very real world problem here. So it says that you want to estimate the age of a skull that's uncovered at some archaeological site if 10% of the original amount of carbon-14 is still present in it. And this is the half-life of carbon-14 again. In these things, right, the way I kind of recommend you do it is, so it's going to be a decay problem. So we want to basically plug in what we know from this equation. And again, this is like end quantity, initial quantity, and rate and time. And the negative is what's going to make it decay, right? It's going to kind of drop down quickly like that. And we know 10% of the original amount of carbon-14 is still there. So the ratio between this and this should just be 10%. So like if you started with 100 here, right, you would be at 10, right? If you started with 1, you'd be at 0.1. And I think that's the one I'll use because it's just kind of an easy ratio, I guess. So we've got one initial amount of carbon-14, let's say, 1 unit of it, it would be down to 0.1 of that unit, right? And then we've got an e in the equation, a negative in the equation. We don't know the rate, right? And we don't know the time. We want to solve for those things, okay? And so this is the kind of common trick in these problems. We basically need to solve for the rate by using the half-life, right? So we know that half of carbon-14, half of 1 basically would be there after 5,700 years. So if you go this long, starting with 1, you'd be at a half, because that's what it means to be a half-life, right? And so now we can use this equation, solve for r, right? Just take natural log of a half, and then it's going to equal minus 5700r, divided by minus 5700, and that's r, right? So if we go and pop this in over here, right, we would get something that we can solve for t, and then we'd be done. So we got 0.1 equals e to the minus natural log of a half over negative 5700 t, right? And so if you take natural log of both sides to cancel the e, right? You got natural log of 0.1 equals minus natural log of a half over negative 570. Really, these negatives will cancel out, right? And then you got a t. And so so now you could multiply by like the reciprocal, and the t would be exactly 5700 over natural log of a half times natural log of 0.1. And this is about 18,934.99 years. So it's an old skull. I don't know what kind of human beings were there that long ago, but yeah, so this is kind of the standard technique for these problems. You know, if it was an exponential growth problem instead, the only difference is this negative would be a positive, and you would still have to use like something like this probably to get the rate, because that typically is always something you're going to solve for in these problems. Sometimes it's given, but yeah, basically plug in. You'll have enough stuff in these kind of equations where one thing is left blank, and then you can just get all the other things there and solve for whatever the remaining variable is. All right, another just kind of important sort of basic fundamental thing for a log unit is just evaluating them. So like this is actually a really, really nice number, and I would never want you guys go into a calculator, you know, down the road to evaluate something like this. I would want you to be able to see that all these things in here are going to simplify really nice. So that's something that's really important. And then in order to solve equations with logs, you need to know like domain things for them. So you got to be able to like look at expressions like this and be able to find the domain of those expressions. So starting off here, so natural log and e are inverse functions, and so these actually will simplify and give you, they'll like cancel out and give you the exponent that's right here, which is really a 1. So that's a 1. And then log 10, when we don't write the base, right, it is 10. It's base 10, it's the common log, and it's the exact same thing. So we have a plus 1 there. So that's all over 2. And then same kind of idea here, log base pi would cancel and give you that 7. So that's a 7. And so now you have 1 minus 7, which is negative 6. And that's it. Very, 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 very nice simplification in here. And you do not want to be going to your calculator to do that kind of stuff. The same way, like, I would never want you to be like, okay, what is square root of 36? Is it 6? You know? I want you to be able to just know some of these fast so that, you know, when it comes to harder problems down the road in math and science, you can do them really quick. Ones like this, at least. So for the domain here, we've got 3 logs, right? And we know that, you know, your basic log is, so there's this vertical asymptote on the y-axis. And, you know, the kind of basic logs look like log growth like that. Or you can have log decay like that. But either one, this acts as the boundary line. And so all logs are, to start off with, you just set them greater than 0. You know, because this is kind of where everything comes from here. So we just take any log expression, and whatever is inside the log, you just set greater than 0. That's it. So we got 3 to do. Let's just start with this one. So that inner one, really simple, x greater than 0. That's all we got for that one, right? We're done. This next log, this natural log, we want log base 2 of x, which is the inside thing there, to be greater than 0, right? So if we did, like 2 to both sides, we would cancel there, and we get x is bigger than 1, right? So we're done with that one. And then the third and final one is this common log, log base 10, and we have natural log, log base 2 of x as the inside thing here, set that greater than 0, do e to both sides, cancels there, log base 2 of x is greater than 1, and then same thing, 2 to both sides, x is bigger than 2. So if you look at what we got, right, we have one option, another option, another option, and whatever we plug in, right, has to work for all 3 of those, right? You can't have it work for just one log and then not the other ones, right? So if you take this one, let's say, compared to this, if you're bigger than 0, you could be like a half, right? But a half is not bigger than 1, so this one is definitely not going to work. That's not going to be okay. And then same kind of thing when you compare these two, right? You could be like 1/2, which is bigger than 1, but 1/2 is not bigger than 2. So that one also doesn't work, okay? So turns out that basically the outer log here is what actually matters. So it's just a coincidence in this problem or something. But yeah, so x bigger than 2, if you go plug that into Desmos, that is where you will see it be defined. It's just anywhere bigger than 2. All right, same kind of stuff here, except there's a fraction, right? And if you have a fraction, you don't want to divide by 0. So we've got to, we'll have to deal with that at some point, right? Nothing wrong with the x squared on top. That's perfectly fine, right? Let's actually just start with the dividing by 0. So we don't want to ever divide by 0, right? So we want negative log base 3 of x squared minus 2 to be greater than, to be not equal to 0, right? And so you're going to get 0, right? If you think of your log graphs, all logs, your basic logs, if you plug in 0, I'm being dyslexic right now. If you plug in 1, there you go, you get 0, right? This is kind of your basic log. So we know that if this inside thing ends up being a 1, that's how we're going to get a 0. And so that's going to be an issue. So what we have to do is take the inside, and we don't want it to be 1, right? Because if it's 1, then we'll get 0 on the bottom. So in this case, then x squared just cannot be 3, right? So x cannot be plus or minus root 3, right? Because both those would make it 0 on the bottom. So that's the divide by 0 stuff. And then just because we have a log, right, we need x squared minus 2, the inside of the log, to be greater than 0. So this is just a nice quadratic inequality, right? We got 2 roots, one negative root 2, the other root 2. And we have like kind of an open up quadratic like that. And if we want to describe where it's greater than 0, right, we want to go, it's an OR problem. It would be x bigger than square root of 2, or x is less than negative square root of 2. So if we put these together, right, square root of 3 is bigger than square root of 2, and negative square root of 3 is more negative than negative square root of 2. So the final answer would basically be just literally putting those together. We would say x just needs to be bigger than square root of 2, but x cannot be square root of 3, or x is less than negative square root of 2, but x cannot be negative square root of 3. And that would do it, right? If you graph this, you're going to see some vertical asymptotes at those numbers. and then it'll only be defined in these regions right here. And that's it. So, really we use this because when we solve log equations or inequalities, we will need to know sometimes to throw out part of our answer because there's some issue with where it's defined. And that would be something like this. So just kind of to build off of that, let's just do the domain first. So we know that there may be domain restrictions because we have logs. So we need, let's just do this one first. So x plus 4 needs to be greater than 0, so x needs to be bigger than negative 4. For this one, x minus 2 needs to be greater than 0, so x needs to be bigger than 2. And lastly, for this one, 4x needs to be greater than 0, or x needs to be bigger than 0. So we can see, based on this, right, that what we're going to need is, we need the most restrictive thing, right? So we need x to be bigger than 2, right? No matter what we get, the only thing I'm basically going to be interested in as the final answer is anything bigger than 2. Bigger than 0, bigger than negative 4 is kind of included in that. So that becomes my main domain restriction in this problem, okay? To solve it, basically we have these ridiculous base numbers that I put in here, but the nice thing is they are the same ridiculous number. So if we were solving this out, what I would do is I'd start off and you got plus logs here, and we know a log property for that is to just, so we got 2, 3, 4, 7, 2, 3. We can just multiply the insides, really. And this just comes out of, exponent properties. We talked about that in another video. So it's really just a byproduct. So it's just a byproduct of exponent properties. Once we get the same base log on both sides, really what we can do here to solve this thing is just do 2, 3, 4, 7, 2, 3, raised to both sides, and we'll cancel that log. 2, 3, 4, 7. Oops, I dropped a 3. Cancel that log though. And then we can just jump down and be like, okay, now x plus 4 times x minus 2 is greater than or equal to 4x. And all of a sudden we just got a chapter 4 quadratic inequality, kind of standard stuff now. So multiply out this stuff. You're going to get x squared plus 2x minus 8. Move the 4x over. Oops. It actually factors. And then, same kind of thing as always. I would draw the little picture. You got a root at 4, root at negative 2, doing something like that. We want to be greater than or equal to 0, so we're here or here. It's an or problem. X is bigger than 4, or x is less than negative 2. This is where domain comes in really nicely. So we have this as a possible answer, but we got to compare it against our domain, right? And so we can see that the only way, the only one of these chunks that would work would be this one, because x less than negative 2 is not bigger than 2, right? And so this right here becomes your final answer. And that's it. So that's really why domain is so important in these problems, because it definitely changes a lot of times the solution. If we didn't do this at all, we would have basically gotten a whole bunch more numbers, right? Anything less than negative 2 would have looked like it should work, but it doesn't. So one of the first things we did, and still one of the most important things, is just to know what these things look like, graphing them. So I just want to do one graph of each here. And when it comes to graphing, what I'm really looking for is a point, general shape, and where the vertical or horizontal asymptote is. So for logs, right, the way I do this is I start at the point 1, 0, and then I just go through all the transformations, okay? So the first thing in here is a 1/2 in there, which is going to, you would think, again, horizontal compression, but it's actually horizontal stretch. So that 1/2 goes, or 1, 0, sorry, goes out to 2, 0 because of the 1/2 there. We do have a negative, so we're going to do some sort of vertical flip, right? Which is really just going to change our shape. And then we have a +3, so we're going to go up to here. So this is my final point, 2, 3. And then if you think about shape, right, we have a natural log. So that's base E. And so that would mean we would have log growth like this, right? But because of the flip, it's actually going to be log, it's going to look like, well, it's just flipped log growth. It's this, okay? It's going to come down. We never did any shifts left or right. And so the vertical asymptote is actually still on the y-axis right there. So basically just draw something that kind of comes down like that. Okay, that's fine. That's it. And, you can always check other points if you want. If you want to plug in 1, you can go to your calculator if you want, just kind of check that it's up here. But really the idea with these problems is to be able to do them without your calculator and kind of get the rough sketch without having to go into all the decimals and stuff. So this is really all I'm looking for. But down here with the exponential, okay, we start at not 1, 0, but 0, 1 right there. And then this -1 in here shifts you to the right one. So now you're over here. And then we have a times by 2, which is like a vertical stretch by 2. So instead of being up at 1, we're up at 2. And then we got a +1, so we end up actually at 3, 1, 3, right? And so that point is 1, 3, and that is like the point I would want to see. This +1, right, is how we could shift the horizontal asymptote. And so we have a horizontal asymptote at 1, okay? And, this number will always represent the shift of the horizontal asymptote. So if it had been a 10, right, the horizontal asymptote would be way up there at 10 and stuff. Then for general shape, we have a 1/2, which is going to be decay, right? And so just draw in some sort of curve that comes in, and it's going to get like really close to that horizontal asymptote, right? It's just going to drop down and get like infinitely close to that without touching it. And that's it. It kind of recaps all the main points of this unit. There's definitely lots of stuff to logs and exponentials. But if you understand all these problems really well, you should be pretty good for this unit.